otherwise I'd be screaming in your ears all the time using that thing. And, so, you could say that there's two general views on the effects of tropical forests vis-a-vis climate and hydrology. You could say, well, you have the public perception on the one hand and the so-called scientific perception on the other hand. And so we can ask ourselves these questions. Do tropical forests increase rainfall? Do they prevent floods? Do they increase stream flows? Do they prevent landslides, erosion? And if you ask anyone in the general public, the answer would usually be yes. If you ask the same questions to scientists, they will usually say, yes, maybe, it depends on this, we need further work, that sort of thing. So there is a fair bit of debate on particularly the hydrological benefits of planting trees and reintroducing forests. And about 5 to 7 years ago, there were a couple of very influential publications by VU and the British government that really were like tree bashing, forest bashing, you know, in the sense that they placed a high emphasis, a strong emphasis on the high water use of forests and the lack of ability of forests to prevent flooding, that kind of thing, and instead forgot to mention the more positive effects of plantations and natural forests, including good soil improvement, good soil protection. So you might say that the scientific perception has become a bit biased in the last 10 years, mostly on the basis of temperate zone publications that are then projected onto tropical situations. The other thing of note is that when we're discussing tropical forests, people tend to forget that not all tropical forests are equal. Some are old growth forests and more or less in balance in terms of carbon uptake and release, water use, whereas other forests, secondary growth, is in an active stage of, you know, aggregating biomass, needing much more water, taking up much more carbon. And then of course we have the plantations, either indigenous or exotic. So it's important to make a distinction between these different forest types. And last but not least, in the discussion we hear very little about the role of soil degradation on hydrology and also soil recovery and its effect on hydrological functioning. Whereas in the official literature, most of this effect, or this aspect, seems to be overlooked simply because in the temperate zone we don't have much severe soil degradation. And so it's got kind of out of the discussion. So I wasn't planning to include the section on deforestation, reforestation and tropical rainfall, but since we have the distinguished Professor Jerry Van Clay in our midst, who is interested in the topic, I thought, well, let's put in a series of slides and see how far we get. We may have some interesting discussion later on. So, most of the discussion on tropical rainforest and climate, or rainfall, centers around the Amazon. That's where most of the work has been done. And roughly the evaporation, so the humidity production into the atmosphere of the Amazonian forest is about 4 millimeters per day, and which equals about half the incoming precipitation. So many people have got stuck on the idea that roughly 50% of the Amazonian rainfall is derived from evaporation from the forest itself. And so you can make a distinction between moisture that's coming in from outside, say blown in from the ocean, then raining out and producing rain, or locally recycled moisture, first evaporated by the trees, then raining out. So people think roughly that 50% derives from the ocean and 50% is derived from actual evaporation from the forest. So if that would be true, that if you would clear that forest, you may lose a lot of of rainfall. Now it's not very easy to do that experimentally. You cannot cut the entire Amazon, although we're trying hard. So people have resorted to models, computer models, simulation models. But that requires the parameterization of the processes at the scale of the forest and the pasture, particularly the production of sensible heat, so the warming up of the atmosphere that produces the updraft for cloud formation, etc. But also the transport of moisture into the air through evaporation. But also important is the functioning of the soil, so that needs to be parameterized in your model in a good manner as well, particularly because infiltration and soil water dynamics determine the amount of water lost through evaporation again. So, and last but not least, and that's the most important thing, arguably, is your model should reflect the large-scale circulation patterns from the ocean to the land, etc. Where is the moisture coming from? That sort of thing. Now it's interesting, without going into too much detail, you need to parameterize all these different things, the characteristics of the forest and of the grassland, but also of the soil and the general large-scale weather systems. But it's interesting when you look at the results obtained with all these different models, that as we move on in time, you'll see that the predicted effect of clearing the whole Amazonian rainforest and converting it to grassland, the average effect on rainfall is a reduction as predicted by all of these models. But what we see is that as time progresses and the models become more sophisticated and stronger and possibly more reliable, you'll see that the average daily reduction in rainfall is declining. So in the old days we thought we lose on average 2 millimeters a day. More recently it's about half a millimeter a day, and even the most recent models still mention a figure like that. So at best, clearing the entire Amazon gives a reduction in rainfall of about 7% instead of the expected 25% if you would apply the 50% model. Now that's what the models say. What do observations say? We don't have information on the total clearing in terms of observation because there is still a lot of regrowth and still a lot of forest left. But we do see that in areas like Western Amazonia, Rondônia, where they have created these large strips of grassland and remnant blocks of forest, they notice different cloud patterns over the forest and over the grassland. Same in Costa Rica, where these large-scale areas that were cleared for pasture definitely have less cloud formation than the forest areas. This here is Nicaragua, where you have rebels, and so no one dares to clear the forest. Therefore, we still have early cloud formation above these forests. Interestingly, because of the differential heating above forest and grassland, the air becomes warmer above the grassland, you get an extra wind that is usually referred to as the forest breeze. Together with the greater roughness of the forest, that often creates more rainfall around the boundary between grassland and forest. So, if anything, there seems to be increased rainfall at these, you could say, at the deforestation arc, as it's often called. But we see some effect on cloud formation, but not necessarily on rainfall, except for that edge effect. If we move to a larger scale, people have taken samples of ocean water and rainfall across the Amazon over more than 1,500 kilometers traveling inland. And what they found was, using some sort of mixing model, they could say, well, this and this a percentage derives from oceanic moisture, and such a percentage derives from locally derived evaporation. Now we'll see that an annual basis, roughly 3/4 of the rainfall, the moisture in the rain, is coming from the ocean, even though it may be thousands of kilometers away. So apparently there is these big systems blowing oceanic air into the Amazonian interior, where it then rains out. And on average, only 25%, so roughly 1/4, derives from local evaporation. But it would be wrong to think that 25% is all from forest evaporation. In fact, most of it is from the very big rivers and lakes that we have in the Amazon. And interestingly, in the wet season, more than 90% of the rainfall is derived from oceanic moisture, and only 10% from local sources, mostly lakes. But in the dry season, this balance shifts. So we'll have roughly half from the ocean and half from the local sources. So the conclusion seems to be that the impact of the forest on creating rain seems rather limited, particularly in the wet season. But this is all pretty recent work, published in 2011. But if you then go to a recent paper published in Nature by Spratler, they found a very interesting relationship between rainfall in Brazil, 2 places, and in 2 places in Africa, and the, let's say, the vegetation to which the passing air was exposed. So, for instance, these lines here show the, let's say, the travel path of the air mass before it rains out. So in this case, if we go here to some place in Amazonia, the rain falling here is transported by air coming from the northeast or from the southeast, etc. So you could then look at the travel path of that air mass and see what sort of vegetation that air mass has experienced. And so you could then look at the total leaf surface area of that vegetation and plot that against the rainfall. And what you see is that you get definitely more rainfall the longer the air mass passes over tall vegetation. So there's a very clear relationship up to about a value of 15. So for instance, if you have a forest with a leaf area index of about 5, then it would take that air mass 3 days to pass over a surface like that to obtain a cumulative leaf area index of 15. That would be about your maximum. After that, it stabilizes. The effect in the dry season, however, is much smaller. So, interestingly, these 2 new studies are contradictory. The isotope study says in the wet season, only 10% of the rainfall is derived from local evaporation. In the dry season, it's 50%. This graph suggests a very strong influence of the vegetation in the wet season, but much less in the dry season. So, what is happening, no one really knows, but further work is required. There could be alternative explanations why there is this relationship between travel above vegetation and rainfall. No one knows. So that's where we're at with forest and rainfall. But most of these slides concern continental situations, like a huge continent like South America, Amazonian forest. Here we are in a, you could say, a maritime setting here in the Philippines and Indonesia. We're all surrounded by oceans, so presumably the effect of the proximity of the ocean on rainfall is even stronger here than in Amazonia. So you may wonder what the effect of land cover actually has on cloud formation and rainfall. Now, I witnessed a particularly interesting event in the Caribbean island of Puerto Rico, where you have mountains up to roughly 1,000 meters high. and clouds starting at about 800 meters. So if you go up these mountains in Puerto Rico, you have clouds at about 800 meters. That means the top 200 meters of these clouds, of these mountains, are virtually always in cloud. But when there came a hurricane that defoliated all these forests, for 3 or 4 months, the clouds were always above the mountains. And that was interpreted in terms of the air being warmer because of, there was no cooling anymore by the vegetation. And after 3 months, when the leaves had grown back on the trees, the clouds came down again. So that shows you something of the influence of local vegetation on cloud formation and possibly rainfall. But what is even more interesting is that if you look at satellite pictures of the top of the clouds, so-called brightness temperatures, you'll see that these clouds are much more active in what you might call the maritime continent. So here in Southeast Asia, Malaysia, Philippines here, and Indonesia, that's the most active zone in the world in terms of upward moisture transport. And the interesting thing is that land cover change will even amplify this. So what people think now is that because of the contrast in temperature between seawater and land surface, we have a sea breeze that pushes the air up the slopes, creating clouds and raining out. If you have deforestation in a situation like this, you increase the temperature contrast between sea and land, thereby strengthening the sea breeze. And so the upward flow after deforestation in this maritime setting will be even stronger, and your clouds will be pushed up even more. And so people have made computations saying that maritime tropics like Southeast Asia, Central America, they're in fact the drivers of the global circulation, much more than Amazonia or Congo, which is kind of an interesting thing, that the Philippines and surrounding countries are generating the world's climate and moisture. So it would be very interesting to look at deforested situations in the Philippines versus forested, and see how it affects the formation of clouds and ultimately rainfall. So speaking of rainfall, another vexed question is about the relationship between forests or deforestation, reforestation and flooding. And every time when we have a big flood somewhere, usually people blame deforestation rather than the excess amount of rainfall causing the flood. So there's basically two schools. There's a school that says deforestation increases flooding, and the other school says no, it's just too much rainfall, it's an act of God. So that's basically where we are. But what does the database say? Well, if you travel around in the tropics and see a lot of places, you definitely come across evidence for very big floods from forested areas. So for instance, here in Bolivia, you see here a guy. Blocks up to 1 meter were transported by a relatively small stream during a mega event falling on a forested area. Other places I've seen too. So you could say that the famous forest ponds that is supposed to absorb all the rainfall and then release it gradually must have its limits too. The forest ponds can be full, and once it's full, it'll just discharge the water like any other land use. But there are, this mainly concerns the most extreme cases. But what about the more regular cases? Well, basically it has to do with the, you could say, the capacity of the soil to hold moisture. And the fact that grassland soils tend to be moister than forest soils already means that these grassland soils have less space to accommodate new rainfall than forest soils. So for the same amount of rainfall, it'll produce more what we call storm runoff. But the interesting thing is that as you move up in size of rainfall event, that difference becomes smaller, such that for the very big events, this difference in storage capacity no longer has an effect, simply because the soils will be fully saturated anyway. They will be full, and so they will just discharge the water. But this storage effect between forest and grassland is only operating when we have, let's say, a non-disturbed situation. If our soil becomes disturbed, then the surface condition also begins to play a role. So for instance, if we have a situation where there is no real soil, and we compare that with the situation where we do have a soil, and we see enormous differences in the response. Because in these areas where we do not have a soil and only a surface that is incapable of absorbing the rainfall, it just runs off. Whereas in the case of a soil, some of the water will be absorbed and released. And so for these two situations, you'll see that there is up to a tenfold difference in response between the forested and the non-forest situation. But it's not a matter of having a forest or a non-forest in this case. It's a matter of having a soil that is actually functioning, or a lack of a functioning soil. So you might say, well, you're going to speak of the soil sponge rather than the forest sponge. The two do not necessarily go together. Because if you have a well-managed grassland with a good soil, that will also have a great absorbing power. That's, you could say, the local effect on flood production or on peak production. But of course, in the real world, we are dealing with larger watersheds. And so you can have rain or degradation in one part of your watershed and dry conditions or nice forest in other parts. So what we usually see is that even if you have locally increased floods in one part of your catchment, the effect becomes smaller and smaller as you go downstream because of the mixed effect of contributions from other areas where it didn't rain at that time. So as you move down, it usually gets diluted, except for the fact when we have a huge rainfall field falling everywhere. So normally you have rain here, but not behind the mountain, as it were, and so the cumulative effect will be less. If you have big rain everywhere, yeah, there is no dilution, it's just addition. And that's what's happening in northern India, Bangladesh, Nepal, where for 3-4 months you have a lot of rain coming in over the entire area. And much of this rain falls on soils that have been saturated already by previous rain. So everything is saturated to the brim, and then if you then have a major storm covering a very large area, then you get a mega flood. And there's nothing about this that you can do except for trying to mitigate the impact by staying away from the floodplain and that kind of thing. There's nothing to do anymore with land use or that sort of thing. At the same time, what we do see is that where rice fields that have these bunds, that typically retain water, areas with a high proportion of irrigated rice fields tend to produce very low peak flows, very little flooding. And if those are converted to urban areas, you'll see a distinct increase in flooding. So even at the large scale. And that is shown here in this diagram from Indonesia, where we're looking at the maximum flows. So you could say the bigger the flows, the greater the flow. In the old days, when the Dutch were still in power, and the post-independence situation. This, of course, has nothing to do with the Dutch presence or the Dutch absence, but it has everything to do with the fact that the people in Java converted their rice fields to industrial estates and cities in West Java. And you can see that the level of flooding roughly doubled. And so I think the take-home message here is that deforestation is not necessarily a bad thing, because if you have paddy rice fields after forest, you still have no flooding problem. But if you convert those rice fields to compacted areas with no absorption capacity that just have to deliver any rain they receive immediately, you can create a serious flooding problem. So urbanization is a big thing, really, hydrologically speaking. The same holds for widespread soil degradation. If you keep burning your land and all your organic matter goes up in smoke, then your capacity to absorb the rainfall will also diminish, and you'll have much more surface runoff. Or if you expose your soils to the power of the rain, crusting, slaking, reducing the infiltration, that's when you're also having problems. And one rare example is from Sri Lanka, where over a 30-40 year period, people have monitored stream flows in an area, showing that as time progressed over these 30-40 years, and when the tea plantations were converted to annual cropping without soil and water conservation, you'll see that in the wet season, gradually greater incidence of flooding and more water. And I'll come back to this later. Increasing the shortage during the dry season. Now you may wonder how much of this is due to land cover change people's doing. Well, if you look at the changes in catastrophes reported over the years, you'll see an upward trend, both in extreme rains and therefore floods and landslides, but also in drought. So you could say perhaps climate change has something to do with the increase in flooding as well. It's not just our land use. Other people say, well, it has to do with the fact that we're now everywhere, we have satellites, we have newspapers, internet, so we have much better information on catastrophes, disasters than in the past. But that may be true. That is, for instance, a very striking decrease here in total numbers of disasters reported since about 1980. The world's really going to the dogs if you look at this graph. But you also see that the number of earthquakes increases since about 1980, or rather has increased and has remained more or less stable. So that is probably because of the greater information flow. If you look at 1980 till 2010, you see that the number of earthquakes has remained more or less constant, but the number of floods and cyclones seems to be on the increase. So the conclusion might be that there are some indications that climate change is actually affecting the number of flood events, and those are exactly the sort of events that we can do little about in terms of land use. So perhaps one argument would be to reduce the global warming and thereby reduce the hydrological activity of the atmosphere. So enough about floods. Let's move to stream flow production. In a nutshell, for a given amount of rainfall, if we subtract the water use to vegetation, that's the amount of stream flow that you have. So if the water use of the vegetation goes up, you'll have less stream flow and the other way around. So if we look at trees compared to grass and crops, we see that they have a greater leaf surface area. That's why we can stand underneath the tree during rainfall and stay dry for a while, whereas outside we get wet. These trees and forests also have deeper root systems that can exploit a deeper soil volume during dry periods, whereas grasses or other crops may turn yellow because they have no access to deeper layers. And also, trees have a more rough surface area, and therefore there's greater exchange with the atmosphere. So for these reasons, greater leaf area, deeper roots, and greater roughness, trees and forests typically use more water than crops or grass. And that's shown in these two general curves here. This is the vertical axis, is the water use of vegetation. The blue line is for forested situations, and the red line for pasture and agricultural crops. And so you see that forests begin to use more water than pasture or crops, around about 500–600 millimeters of rain. Below that, all the water will be consumed anyway. Above it, the difference gradually increases with the amount of rainfall, possibly because of rainfall interception effect. But the most important point is that trees will use more water than shorter, shallower rooted crops. Now the way to, you might as well skip this one, the way to investigate that is through so-called paired catchment experiments, where you monitor stream flow from forested and non-forested areas and look at the effect of changing forest cover. And what we see is that the more forest we remove, the more extra stream flow we will have. So the zero line here is the amount of stream flow that we have under forested conditions. Everything above is the extra stream flow generated after forest or partial or full forest removal. So as you remove more forest, you will have more stream flow simply because you have less water use than before. At the same time, if you remove all the forest, there's an enormous variation in reported results. The extra stream flow may be as little as 100 millimeters or as much as more than 800 millimeters. So apparently there is quite a variation between situations and sites. And of course, one idea would be to plot that against rainfall. You can imagine the more rainfall, the bigger your extra effect. But what you also see is that for a given amount of rainfall, the extra stream flow may also be very variable. So it cannot be just the rainfall, it must also be the actual situation. And the obvious thing to think of is the effect on the soil. And of course, when we start logging rainforest and dragging out the logs, we get compaction of the soil, such that during intense rainfall, you can have huge amounts of surface runoff. This is not a stream, this is simply a slope in Malaysia during rainfall, heavy rainfall, on a tractor trail. So what it looks like is that soil effects are also very important when it comes to assessing the change in stream flow. So not just forest or non-forest, but also the condition of the soil. So essentially there are a couple of reasons. We remove the forest, we also remove the rainfall interception. We don't have that big canopy anymore, we just have small plants. We have shallower roots, less leaves, so also less soil water uptake, particularly in the dry season. We also, because of this lower water use by the vegetation, the soils will be more moist, that is less uptake, And so these wetter soils have less accommodating power and so produce more response. And of course, if they're also disturbed and compacted, they'll also produce more surface runoff. So these are the reasons for generating more stream flow after deforestation. And I'm not saying that I'm making the case for deforestation, I'm just saying we'll have more stream flow in total after deforestation. But the important thing to keep in mind is that after forest removal, we can have different situations. If you look at these two landscapes, both of them are virtually treeless. But here in West Java, in Indonesia, you have these neat terraces where let's say the hydrology is more or less benign. You go here to Nepal, overgrazed slopes, almost no trees like here, but totally different in terms of hydrological behavior. So the upshot of this is that it's not the amount of trees perhaps that's there in terms of hydrological functioning, but the state of the surface, the state of the soil. So it's very important to keep in mind that the post-forest situation represents all sorts of different conditions. And so, if we have a situation where the grassland after deforestation is well managed, or cropland after deforestation is well managed, then the annual flow typically go up after deforestation and, be more or less stable over the years, as long as the management is maintained at a good level. Whereas if the management would be poor, you would expect this line to go up because more and more water is running off just like that because of poor management. So what we see is that if we remove the forest, we'll have more stream flow, at least according to the data presented. But there may be one exception. Oh, wait on. So these data, or this situation, is typically for well-managed land. But at the same time, if you go to the tropics, you see that most of the Philippines here is red, like many other areas, including Mediterranean. A large proportion of the planet is actually potentially subject to soil degradation, or at least there's a major hazard of soil degradation. So that means that you really need to manage your land well if you want to avoid